Okay, is this, yeah, so thanks all for coming. This is the What to Do at ADF session. I'm Daniel Thompson. I'm in the kernel working group on the Android upstreaming team. And just to give a quick idea of the running order, this is a discussion session. I would have called myself an audio guy about 2 years ago. I'm learning other things now, but I started out as an audio guy in a television place. Is that, yeah, that's louder, yeah. So yeah, I've been asked as part of the Android Upstream work to look at ADF, which is a big difference in terms of code, lines of code between this. This is a discussion session, and I've got a short summary of the ADF data flow, which I've pinched from Greg's presentation at Plymouth, just so that everybody's on the same page about roughly the structure of ADF. And then it is a matter of trying to work out the mechanisms we can use to upstream those features. So ADF is relatively new in the sense that I think it first came in the 3.10 AOSP kernels, and it's a DMA-centric, and it's very strictly DMA-centric plumbing framework to connect the hardware composer into the kernel. I described it's focusing heavily on data, if only because that was half the time spent in Greg's presentation, and it's actually audio background. There's data and there's metadata stuff that tells you what to do with everything, and the focus in ADF as it stands at the moment is that it's there to get the data, all the bandwidth stuff across the chip, and its metadata is using the binary blob technique, so that there's private communications between a driver and its manager in the user space. And its obvious most fundamental feature is it's atomic, so all the buffers hit the glass in one shot. And that's the key reason for the atomic in display framework. In principle, I don't know if it's been played with, but in principle it should also connect to something like Wayland Western. Your Wayland Western's render model is sufficiently similar to Android that it should be possible to write a Western backend that pushes everything out via ADF.
One difference.
There we go. With a Wayland compositor, you tend to not have a driver-specific part in user space for the mode setting. So to the extent that it depends on driver-specific blob data for setting up the scaling and so on, that might be a limiting factor. But
I'd certainly view it as a good thing that Wayland can focus on having one backend. Although you're seeing people like Raspberry Pi guys write brand new backends to point at the Raspberry Pi hardware and things like that.
Right. So for Weston, we're actually seeing multiple different backends in addition to the KMS backend. Although Eric Anholt's writing a DRM KMS driver, among other things, for Raspberry Pi. So probably eventually they move to a standard. Now, I mean, the tricky thing with the Wayland compositor is that Wayland is not one thing. You have GNOME Shell Wayland compositor, Enlightenment Wayland compositor, whatever they call the Qt one, and so on. So, yeah.
So I'll unquestioningly agree that I think it's a good thing to have the smallest number of Western backends that we can achieve.
Right.
Okay, yeah, so just to this blue box around the foils means that I've pinched it from somewhere. Most of the pinching has happened from Greg's material, but I have actually pinched from a couple of other places as well. So just to let you know the credits and so on. So this is the buffer description structure in ADF. Are you happy for me to be saying all this? So the buffer is, I actually prefer to them keep backwards. I prefer to think about the post routine, which is the thing you're going to do your octal on to pass into the kernel. It takes a list of buffers. The buffer mappings are generated, it's internal housekeeping for ADF, and at the bottom of that you get the custom binary blob which describes the Z order, the alpha, the structure of the frames, and how they should be manipulated to go on the glass. And obviously the biggest structure in there is the buffer structure, which is this one. It's got the overlay engine that you're pointing the buffer at, its size and pixel format. And the number of, I have to say that the one thing I didn't get when I looked at all this was the planes, because having an array of buffers and an array of planes is a kind of 2D structure. What was the, if you're constructing an image, how to choose which bits you put, why would you send more than one plane at once in a buffer? So I said it was a discussion session, I didn't mean it.
So the reason why you would need to have multiple planes in a buffer is it depends on your hardware. Very frequently, if you're feeding in, say, YUV data, often on mobile hardware, you don't want to convert that into RGB. So you actually feed the separate Y, U, and V planes straight into the kernel, and then your driver just writes the locations of those out into the hardware. And so depending on your hardware, those may actually be separate buffers. They may be pointers into the same buffer, in which case you're just going to duplicate the DMA buffs, like the same thing each time, and just have different offsets and pitches.
Okay, I was a TV guy to pick that one up. Yes, I see. So that would be formed into a single image. So a buffer is still a single image. Okay.
Yeah, I apologize. The name ADF buffer is a little bit deceptive, and probably ADF image would have been a little bit clearer, but that ship has sailed.
Okay, and thank you for that. Sorry. And then the bottom of that we have the fence, which is marked as optional, but it's pretty fundamental to Android's display optimizations. So
yes and no. So you do need to have some kind of, to do stuff in Android optimally, you do need to have some kind of synchronization. At least in the current version of Android, I don't know what the future plans are, but the current version of Android, you can do that all implicitly inside of your drivers. And for instance, that was the way it was done in earlier versions of Android pre-Jelly Bean. But the idea is that if you do it explicitly using the sync fence mechanism that's in the Android kernel, and then it is getting upstreamed as part of DMA fence, then if you pass that fence in, ADF will automatically handle it for you. And so you aren't responsible inside your driver for waiting for those fences to fire.
Okay, so I've only got one more slide of Greg's to look at, which is this is actually two of your slides originally. This is the sequence that happens during an atomic post. So the buffers are all imported and sanity checked, so that there are all the generic activity that you could do on a buffer is done in the framework before the driver gets anywhere near and looks at it. The framework will have already checked that the buffers are correctly sized, that the DMA buffer be brought in and so on, everything else. But then you do pass it to the driver, because there are certain hardware-specific checks that you simply can't do with the generic lab. But when the driver gets it, it's gone through this. The validation hook has that particular form. And once the driver gives it back, it gets placed in the queue to be displayed. In the validation code, the driver is also able to do pre-work. So it is able to even create a shadow register set, things like that, so that when it gets to the point of posting, it's able to do that cheaply. So the ADF worker will dequeue the config and wait for the fences to fire, and when the fences fire, you go back into the driver and it will then update the hardware state. So it's the driver's choice where it does the pre-work, whether it does it when you validate it or when you post. Yeah. But it does give you the opportunity to set almost everything up before you let it go. And once you have posted, that's now destined to hit the glass, and you can start to free up the old buffers. And then finally, there's a callback into the driver to clean up the internal state, and that's well, from what I saw, I felt that was kind of the heart of what ADF was doing. It has things on the side for mode setting, which are obviously necessary. It has, going through this, it's got frame buffer support to do legacy bits and pieces. But for me, the essence is that act of doing the atomic post is the key bit. This is a good opportunity to disagree if you think I'm wrong about it.
No, I mean, a lot of this is just motivated by stuff like, yes, there is mode setting sort of on the side, and that's motivated by the fact that Android doesn't really do a whole lot of mode setting. You set an initial mode and basically stick with it for the lifetime of your system. You know, certainly there are areas where I think KMS covers, where KMS is much more sophisticated for things like that, and this is sort of motivated by I wanted to pin down the things that Android specifically needs, and that's primarily being able to update display atomically.
Okay. So just in case anybody wonders why we might care about this, I mean, Android upstreaming is by its nature looking at the differences, and ADF does significantly overlap with parts of DRM KMS. DRM is an interesting space. Having grown up with PC graphics cards, it combines in one acronym the GPU memory passing and the compositor. If only because on a traditional PC graphics card, the compositor was very weak, and so the idea it was something separate was hard to understand. What happens when you move into the ARM ecosystem is that the compositor is a separate cell defined by a separate person. It is, in essence, two things now. You have the GPU and you have the compositor. And in this case, so ADF is essentially a compositor driver. And the DRM, there is some talk in the DRM community of trying to split so the user interface to DRM into render nodes and composition nodes. That's what you're saying. All right, so I listen to that. But yes, to be clear here, so ADF is essentially a compositor driver and a framework to help you build them. And so why do we care about that? Is ultimately that overlap means that it's harder to get drivers that are sitting on regular Linux working on Android, which is difficult for people for whom Android is not the dominant operating system, where it's part of a bigger ecosystem. So SOC vendors, particularly enough to say I work in the TV space, and TV vendors are still waiting for Android to come and roll over everybody else. But until that happens, we have the wider Linux drivers to concern ourselves with as well. You hit the same problem going the other way. The mobile vendors make it more difficult for them to look after niche spaces in their ecosystem. And what's essentially happening is it's particularly difficult to bring up when you can't bring the graphics up because you've got the wrong compositor to drive, things like that. And even companies that have kind of worked really hard on upstream graphics are thinking and looking, saying, actually, yeah, we've got to create two drivers for our compositor. So that's why we care at the moment. And also from the point of view, we suspect ADF is going to be one of the biggest lines of code contributor to the delta between mainstream, particularly when you include the vendor kernels, because ADF, in addition to its framework account, we also have to add the lines of code in on the vendor kernels. So yeah, we see it as a big number of lines of code. We don't like
Yeah, it's always pretty small.
it is, yeah. I remember reading about the lines of code reduction in was it the Samsung driver? Dropped quite a few thousand lines of code as it was ported from one to the other. But I mean lines of delta, you know, diff stat lines, rather than burning up lines of code for no reason. So one thing to look at, of course, is the community activity in similar areas. I had a quick review of this, and I had to ship my slides out 2 weeks ago, and I've missed one. But anyway, so some of the interesting activity going on in this space is inside Linara. There have been a number of projects to have a hardware composer HAL that sits on top of DRM KMS. So it's been round the houses. Currently, I think Benjamin is one of the people pushing it quite hard. And that's reaching the point now where you've got boot demos. You can get very close to having this working. And because we're in a space where ADF is designed to support what Android needs, and it's a really, if nothing else, it's a really good documentation of what you need to do to drive an Android display effectively. It means that having other hardware composer implementations is really important if you want to play in this space and actually do any work to go further, because you're proposing alternatives without demonstrating them running on Android is rather pointless. Rob Clark behind over here is had a it gets called multiple names. I think it's atomic page flip or nuclear mode set, and it gets crossed in and out as various bits of coming piece. I'll try to summarize it. In essence, it takes more or less the entire of the DRM API and allows it to be set as properties rather than direct octals. And then that means when you have converted all the legacy octals into properties, you can provide a list of property changes going into the kernel, a list of properties going into the kernel, and it can atomically rip down the whole list in a single system call.
So, okay, you actually have that slightly backwards. I mean, approximately upstream, I mean, it's kind of all one thing, but we've been calling atomic mode set and nuclear page flip. Just so, just a little bit of background. Upstream and on certain various desktop graphic systems, the atomic mode set is actually the key feature, especially with the coming, DisplayPort, multi-stream. But also we have some hardware that has weird constraints like, this, well no, actually the generation before this laptop could drive 3 displays, but 2 of them had to share a pixel clock, and that's something you couldn't really deal with properly if you're not doing your mode set across all outputs in one shot.
So yeah, one of the things that the property system's giving us is that idea we can
but it's
roll back when it fails halfway through is all.
Yeah, it comes down to all or nothing style interface. One interface where you do one ioctal where you can set everything, and the kernel can say yes, I can do this, or no, I can't.
So there's that work going on in the ecosystem. It's all relatively small, but I picked it out because it's interesting to see other uses of DRM in Android. So fairly recently, this guy picked up some work from the Android x86 project and took it and delivered it to the upstream libdrm so that its build system was ready to go on Android. Now on Android x86, they're essentially not using any composition hardware that I'm aware of. It's all the compositions done on the GPU. So that libdrm builds for Android isn't directly related to what we're talking about here, but it is that idea that we have other people using the DRM API in the Android ecosystem. And I've rather cheekily quoted Greg. I didn't know if you were coming or not. So I was, when I prepared the slides, I wanted to have some input from you, and this was the best I could find. You're welcome to disclaim these where they're not up there to pressure or anything, but Greg was offering the idea that if there's community interest in this space, then he's anxious to see us try and merge some of this stuff into KMS. I don't know if that holds true or not.
Yeah, so that was true when I said it, and it's still true now. We're getting some of the same feedback from vendors. Chrome OS is based fairly heavily around DRM KMS, and vendors come to us and say, why do we have to provide 2 graphics drivers or 2 display drivers for Google? Why can't you do a single thing? And I'd like to think the implication is, why does Chrome OS use KMS instead of ADF, but maybe it's the other way around. Certainly, I don't think it benefits either us or the community to keep having 2 separate things in, for the lifetime of these systems. Like, I think there's a lot we could, both Android and upstream could benefit a lot from having a single display system. Like in our case, the more code we can provide to help vendors write both their kernel code and their user space Harbor Composer HAL code, like the more code that we can write and make sure works correctly, sort of the better for us. And if there's only a single display system that people target, we're not interested in mandating that they use a particular user space to kernel interface, but we can provide them with carrots and sticks. We can provide them with the carrot of here's code for you, and we wouldn't really provide them with a stick, but upstream could provide them with the stick of we're taking FBDev away, or we're taking whatever they're using away.
Yeah, it's one of those. I remarked this with the DRM space. That obviously, for so much of its life, it's been dominated by free PC implementations, and the compositor was not really a very important part. It was not the place where the bugs were going to go. You've got a GPU and a compositor, all the bugs are going around the GPU. Right? So they're expecting really high caliber driver writers, and the drivers are absolutely trusted to kind of do the right thing. And they offered help, but if the driver writer doesn't want it, that's fine. And that's a philosophy that is much harder to apply to the big Android ecosystem, where you've got 20 different SOCs. You've only got 3 GPUs, but you quite possibly do have 20 different compositors. It is a big change in that sense of who's taking part in the DRM ecosystem. And it means things like the helpers and other bits are definitely growing in importance, certainly from my point of view.
Now having said that, we have vendors come to us and talk to us about their experiences using like ADF and KMS, and the general consensus is that ADF is much simpler to implement correctly, and so I think that this proves a sort of a niche that ADF fits in, and I think the solution is not to sort of kill off what ADF is doing, it's to make KMS for ADF style, where the impetus on the driver developer is smaller than it currently is. And I think of ADF sort of, apart from an implementation that a lot of people are actually interested in using as is, I think it's also a good example of the API I think that would be good for, at least for our ecosystem, for KMS to move closer towards. So I think it sort of, it presents a very simple API that I think would work both for Android and for Wayland. I mean, yes, there are, for Weston, and yes, there are some differences about, what is passed in is sort of binary data as opposed to a list of properties, but I don't think those are huge differences.
Yeah.
And I think those could, I know Rob has proposed to sort of resolve some of the API issues around the property stuff, around maybe doing helpers that would help you maintain some of the state more, because ADF, ADF has the style of you pass any complete specification, the nuclear page flip, or is it nuclear, what's that? Yeah, it passes in a delta basically, which we feel is not necessarily the simplest way to deal with, but you could probably work around that with helpers that maintain the state for you. It's a relatively minor point, but it's one that I think unfortunately people have focused on maybe a little bit more than we needed to.
Yeah, I'm going to push on a little bit because I have a few headings
sure.
set up to cover it. We don't have to follow my template over there, but yeah, let's move on a little bit more. Thing that I said so I forgot somebody. The person I've forgotten is Martin Lankhorst, who's been working on the DMA bus fence support. And while that's not directly related to compositors, it's clearly in this space because one of the key things that you've got in ADF is the management of the sinks and the fences. And so to get the upstream DMA bus fence stuff in and it's part of the story basically. So that should have been on here as what's going on in the community, but unfortunately I didn't think of that until a couple of days ago. So this is the kind of the straw man slide where we could see disagreement. I kind of hope we don't, but putting big blocks of code into the kernel as an upstream activity is incredibly hard. It is resisted by maintainers left and right. It's how the Linux community works. It's with evolutionary steps. And the question is what you draw from that, and I have to admit, what I drew from that is that to some extent we treat the ADF motivations features, I hadn't thought about the look and feel quite so much, but that's certainly something we can bring in scope, as a shopping list. It's the way I think you can move forward. You look at what ADF has, and you take the really great bits and try and move them over. That then means that the rest of the sessions identify the really great bits and the other bits, which is why we talk about the properties and the other bits and pieces as part of that story. So I've pinched Greg's slide here just to have some thoughts about headings. The reason I did that was so that I could put some headings on how these because that was a list of critiques of DRM KMS. It's not the whole story, because of course ADF also has features that are arguably not critiques of DRM. So it was a slide that allowed me to pick up some headings from this. The particular thing that was...
I was going to say, I guess that's from your from last year. So since that time, we've landed the DRM bridge stuff, which helps us deal with at least some hardware. I mean, currently it's only CRTC encoder, single bridge connector, but it doesn't seem unreasonable to support multiple bridges for. So like a bridge might be something like if you have a external converter chip of some sort that says like goes from LVDS to HDMI or DisplayPort or something like that.
You bring your microphone close.
Oh, sorry. I was just making a minor note that we've expanded the KMS object model slightly to introduce this bridge object since this was written.
Wish I'd found that while I was just saying.
Sorry. Yeah. Okay. That's all I was going to say.
So these are some headings I was going to suggest we could. The reason I wanted to move on while you were speaking a minute ago was that I've drawn quite a strong differentiation between the driver lines of code count and the user space facing API. And I think they are separate topics. I think we should discuss them both. But there's a relatively good story in DRM with the helper functions and making the helper infrastructure better and better that drives driver lock down and driver lock count. I should be a bit more awake for that. Oh, it's lines of code, isn't it? Yeah, sorry, that's fine. So yeah, it can drive the lines of code down in drivers quite effectively with the helpers. But changing the user space is much harder. So I'd like to think, I know it's the same thing for Android, because on one side of the user space you've got to tell it what to do, in the driver space you've got to do it, and they are co-developed across the HAL quite often.
Right, and I mean,
upstream we can't think like that, unfortunately.
Requiring user space change is not even an option upstream. I mean, with the upstream kernel we have constraints about backwards compatibility and so forth that that make things more challenging. But I mean, ideally, all of that's handled by DRM core. So, DRM core might end up with lots of code, but hopefully the drivers aren't dealing with that quite so much.
So if these slides aren't contentious, I can actually move on to the topics individually. Like I said, I was hoping they weren't contentious. So the first place I've looked at is the gaps. This is actually partly, I've got some time to spend on this. So the main reason for this is that I've got some cycles opening up, and one of the things I want to get out of this session is the top item on the shopping list as being the thing that I should actually spend some time doing. And gaps is one of them, in the sense that when we have gaps between some of the thoughts about DRM are to do with difficulty of writing driver, to do with the model not being as rich as it would be desirable for it to be, which is fine, but if we haven't got a sandbox to play in, because we haven't got fences, because we haven't got custom pixel formats, if we haven't got the right place to play, that's clearly the thing we have to do first, in my mind. So that's why I have gaps here first. And the two big ones that I picked out, I think the DMA buffer without gem is actually in the wrong heading, but so the custom pixel formats are there, which I feel for YUV hardware and things like that. How does that overlap with V4L interfaces? Have we any?
V4L is using.
YUV is usually V4L.
Yeah, V4L is using 4CCs as well, but I mean, DRM KMS uses 4CCs as well. There's a small thing missing to allow completely custom 4CCs through, although I think it's not an unreasonable thing to add, just no one's added.
I also want to add, it's not just a YUV thing. Increasingly, we're seeing vendors who have, for instance, will actually let you pass block linear laid out buffers generated by the GPU straight to the display, or that may even use lossless compression. And so those are effectively custom RGB pixel formats.
Yeah, okay.
So probably all of the desktop GPUs support compressed frame buffer, but it's kind of handled under the hood internally within the driver. It's actually something I've started thinking about the other day. Ideally you don't want to have an explosion of every 4cc times every tiling format, but I think maybe it's reasonable to allow 4cc's for formats that are used on the interchange between devices, because that's a much smaller set.
I'd quite like the idea of allowing the driver to provide some help to the helper, and then letting the helper do the work, which is effectively the pattern used in ADF. That plug-in validator is providing help to the helper almost.
So to be honest, I'm not worried about an explosion of a crossfire between the block linear formats and the pixel formats, just because in practice we don't see that. For stuff like YUV, they just generate it in the canonical format, because typically your GPU is not going to be generating it. You get YUV from when you're decoding like a movie or whatever. And then for RGB...
You do end up with custom YUV formats, and the reason for that is that decode block movements like custom formats of the block movement.
But again, that's usually restricted to, like, you don't get that times multiplied a bunch of different memory layouts. You effectively get, oh, they've changed the way that, the size of the U, and I can't think of anything off the top of my head, but they're extremely similar to the existing YUV formats, and so you don't get this explosion there either. And then again, with block linear formats, typically it's like, oh, you have a block linear RGBA 32-bit, and that's it.
Also, if we were to get an explosion, that's because the SOC vendors have created funky hardware, and we've still got to support it.
Yeah, I mean, I actually just started looking the other day at how to get output from a video decoder on one platform into Mesa, and I mean it's the same thing. There's an EGL image extension for that, but that means needing a custom 4cc because there's no other parameter to pass tiling format. So so in the past, when custom 4cc's were proposed for DRM KMS, it kind of got shot down with the, hey, this should be some orthogonal parameter to prevent this explosion, but I was actually just thinking of proposing to relax that a little bit and allow it where you have tiled formats between devices. I mean, in GPUs there's a lot of different tiled formats used internally, but I don't think we need 4cc's for all of those.
Can I ask, have we got some names of hardware devices? I have, our hardware used to use custom formats, and because they're actually inefficient to scan out, they're really good for the decoder, but they're inefficient to scan out, so we actually make the output format one that's efficient to scan out, rather than one that's efficient to author. So I don't have hardware on my desk at the moment that has these properties. Have we got some names?
I mean, the hardware I was actually looking at is Snapdragon 600, because it's for my Arduino work, and someone was working on a hardware decoder and said, hey, there's this custom tile YUV, we want to get it into to render with a GPU. So, I mean, that's not specifically about DRM KMS, but it's the equivalent thing. We need to describe it as a 4cc. So V4L already has a custom 4cc for that. In user space for GStreamer and that sort of thing, they have a custom format string they use, which is now analog to a 4cc. Yeah, so I'm going to revisit
It's
that.
a hard thing to upstream without saying it's for this driver. You don't just throw something into the core of DRM to provide a custom CC format without at least some reasonable piece of hardware for the code to exist in the kernel.
So one reasonable thing, I think, would be to allow drivers to provide a list of custom 4cc formats that they support. I'm a little bit more worried about the Mesa bits because that gets plumbed through all of the Mesa EGL, but
anyways, I do have something. I was going to mention really quickly on the fence thing that there are people even talking about, now that we have the fence stuff landed upstream, of, well, maybe even the DRM helpers for Atomic could support dealing with fence stuff. And there's people even thinking about how to do explicit fence in certain cases, but making that coexist and be backwards compatible with user space and stuff is kind of interesting. But
just have to express the fence, I mean.
Yeah, but I mean, definitely, I mean, if there end up being many DRM drivers which need similar helpers, people are open to, I mean, at the real simple end of the hardware spectrum, the CMA helpers are a good example. You know, it's fairly easy to write a driver for a real, you know, DRM KMS driver for really simple helpers with the CMA helpers.
Yeah, I have to say,
I mean,
I
that's-
did spot that in the view that the CMA,
Yeah.
it's Benjamin's driver, the attachment to do things like the gem mapping and the boilerplate for the frame buffer and all the other bits and pieces is 2 lines. It's 2 courses, 2 helpers, and that's done.
Yeah. No, I mean, I think a
Yeah.
lot more hardware now has IOMUs and stuff like that, so that maybe the CMA helpers aren't appropriate necessarily for all hardware. But I mean, it's an example of if there's common patterns, we can refactor them out into helpers.
Yeah, I'm certainly of the view that helper for, I mean, there aren't that many platforms that, again, on my desk with IOMUs today, but helpers to do the same kind of property for IOMU. There's 2 really common patterns in the R community. There's either going to be IOMU or CMA-based systems. It's only really when you have to do multiple DDR banks and bandwidth juggling that you start to see other allocation and mapping techniques become important. So you certainly helpers for IOMU did strike me as a big, worthy thing. Okay, so I've only got sort of 50 minutes left. 2 other headings. So just modeling the hardware. The idea is that Rob's already mentioned extensions to it, but KMS provides a fairly formal model of how pixels flow through the system. And it has to, because you need, if you're going to have things like West in the user space being generic, then you have to have a model that the user space understands so it can figure out how the pixels hit the glass. If you are not putting, and this is again the difference in the Android ecosystem where the user space has intrinsic knowledge of the hardware it's driving, it would be very desirable for us to be able to have things like Western that have no particular driver knowledge. Quite often special paths and special features. But
yeah, I mean, the ideal thing in my mind would be to have something kind of a little bit analogous to how GL works. And that was kind of the idea with the properties. You could have driver custom properties, user space can look at it and say, oh, the hardware supports this thing, I'm going to do, you know, I might use a different code path, or I might do something special. But, you know, if you look at a GL game or a game engine, you know, they have very different code paths for different hardware, but it's kind of figures it out at runtime by querying the driver and looking at the extension strings, or in this case, the list of property names that are there.
So I think where the display differs a little bit from something like GL is that the constraints that exist on display hardware on like mobile class devices are often extremely cruel and unusual. You know, they may be things like, oh, you are limited to this many number of planes, and this is real hardware we're seeing. You're limited to this many number of planes, contingent on your display resolution and also how many of them are overlapping on a given pixel. Like things like that, I can't think of a way to represent generically. And my concern is even if we tried, like some hardware manufacturer will find an even more bizarre way to place constraints on how you can composite things. So I actually like Android's approach here in that it's up to user space to know how to lay things out, and I understand that creates a lot of problems for something like Weston. And I'm wondering if, there already exists in libdrm some backend specific code for buffer allocation. I'm wondering if you could push something similar into libdrm for vendor-specific composition, sort of like we have in the hardware composer HAL, except instead of just shipping one .so file, you ship a .so file that knows about a bunch of different things. I mean, yeah, yes, that creates a burden on the user, and that they need to know, they need to have an up-to-date libdrm or libkms or whatever you call it that knows about their hardware. I'm not sure if that's a giant deal in practice. Like, they need to have an updated kernel driver anyway, and from our perspective, that from the Android perspective, you just ship the right version with your device, and again, from the more traditional desktop Linux perspective, you need kernel support for that anyway, so I don't think it's a huge constraint to also say you need user space support for it, but I'm not the one who'd have to make that work.
The question to some extent is also how much is weird, crazy stuff from SOC vendors and how much of it is common. I mean, the classic one, the compositor, is downscaling. As you downscale, then in a single part of vertical sweep, you have to suck out the whole frame, and you've bodied the bandwidth. And that's common to all compositors. It's the limits of the memory bandwidth are not even well understood by the SOC vendor sometimes.
So unfortunately, to answer that question, I'd kind of have to fully describe what some of our partners do in their display hardware, which I'm not going to do on camera. Let's just say that anytime you make an assumption about the way display hardware works, some vendor will challenge that assumption.
Yeah, I mean, I think, well, there's two different things. There's one, getting something to work, and two, getting it to work optimally. I think you're right. If you want to fully exploit the hardware to the maximum of its capabilities, you probably need to have some sort of user space compositor API that has a driver-specific module that knows these sort of things. For something like Weston or a KMS-based Wayland compositor, I think for the upstream folks, the first step will be just having something that works at all, and without knowing what hardware it's on, and then if there's some common hardware or something like that, then you start go, oh, okay, I'm on XS, I'm going to do this, or something like that.
So whereas video surface is out of scope.
Yeah, whereas I think Android is not really caring so much about the, well, it works, but it's not working optimally step. You kind of want to go full bore from the beginning. And I think to do that, then you do need something in user space that knows about the hardware.
Yeah, I think that would be a pretty good compromise to be able to take sort of a slow path on every single device, and then the fast optimal path, user space needs to know something about the hardware. Like in Android, yes, we do care a lot about taking the optimal path just because we are so hardware constrained. And I think sort of the reason why we haven't had to deal with this before is the hardware very rarely intersects. But I suspect we're going to start seeing more PC class hardware looking like the mobile class hardware because the major players in there are also getting involved in mobile.
Okay. So I'm conscious I've only got 5 minutes left, so I think we might want to move on to the other headings. These were chances. That was something we could put up some visual aids if we had to discuss the differences in model, but I think that was unnecessary. We've already talked about driver lock count.
One thing I noticed in ADF, so it didn't seem like you had a way to do a mode set with the same buffer on multiple displays because you don't have an XY offset.
So yeah, we can discuss that later. But again, the name ADF buffer is kind of deceptive. It's sort of a description of here's the memory buffers and where you want them, so you could pass in the same buffer to multiple different outputs.
You have you'd have to create 2 ADF buffers for the same underlying buffer, where KMS you create 1 DRM frame buffer and use it in both. And that's mostly only important for X, because X, that's how it does multi-monitor. It's kind of old-fashioned that way.
I suspect we've already talked about most of these in terms of driver lock count reduction. I think the things like the gem boilerplate have got convincing stories to help us in most cases. Not necessarily written, but the example of CMA shows it can be done at the very least. The properties was the interesting one, I think, left. There was a comment earlier about help us to manage the conversion of property processes into a data structure. You're thinking of kind of the property descriptors telling you where to poke, or?
Well, so I mean, there were 2 separate things here. The first was, do you have a standardized way of laying out this information versus just having it in a blob that's vendor specific? And we just went with the blob difference, and my thinking was just, okay, you already have to make vendor specific decisions about how you compose the screen, so also requiring this particular description to also be vendor specific is not a huge leap from that. But like I said, if we want to move towards something more generic, we could use something that is a more standardized property, key value based system. The other issue is that the copy update commit is, again, a slight burden on vendors, because in practice, both Weston and the Android hardware composer HAL just pass any complete description of the state, and so your kernel needs to be able to duplicate state, and also in addition, user space needs to know something about state so it knows what it's tearing down and replacing it with. Again, on both sides, both the kernel and user space, that can be dealt with helper code, so I don't think it's it should be a huge point of attention, but
yeah.
It seems to me, my understanding is the ADF is not necessarily use multiplied buffers for multiplied display. It depends actually. If this buffer goes to hardware composer, it will use the application buffer directly. So for multiplied display, actually it's same buffer. So if this display go to sysfinger for composition, that's by nature we have different display, because we use different frame buffers for different display. So in that case, we are using multiple buffers for different display. But
right.
In the first case, we use the single buffer, that's the AP buffer.
So what I was referring to specifically is you need the struct ADF buffer, which again was not a very good name, is basically just a list of here's the DMA buffs, here's what's going to scan them out, and here's the position on the screen. And if you have multiple, images that you want to scan out on different devices, on different displays, you will have to feed those DMA buffs into multiple struct ADF buffers. Like you'll need one for display 0 and you'll need one for display 1. That doesn't mean you have to actually duplicate the memory backing that. It just means you have to duplicate the struct describing this is what I want scanned out here. And again, that's why I think struct ADF buffer is probably not the best name, because it implies that that's what you have to do.
Yeah. So back to the property thing. With the atomic stuff, it's collecting everything up into state objects per plane, CRTC, and, well, connector now. So the driver doesn't really have to worry about all that stuff. When the driver, when it's time to pass the update down to the driver, it sees the entire collection of state. There is some discussion still about, I think for mode set it makes more sense for user space to set the entire state, and anything it doesn't explicitly set gets reset to default. For page flip, maybe the inverse makes sense, but those things could go either way if someone comes up with a convincing argument one way or another. I mean, those are not locked in stone yet because we don't have the ioctl upstream, so we can change.
Yeah, I mean, that would be fine with us.
Okay, well, I have to note the clock is running out at this point. So the thing we haven't talked about is user space complexity, if only because we've already mentioned that it's really hard to take things out. That's a nebulous quote from Linux Weekly News, but it's in essence just pointing out how hard it is. The only aspect I was noting to explore is that DRM is capability based as an API. There are capabilities you can choose not to have, although I could not see any that made sense to withdraw. Given gem is what provides DMA buff import export, I didn't see there was any subset I could see that was worth considering.
I mean, there is tons of legacy. I mean, stuff for user mode setting and stuff, but we've been kind of partitioning that off into its own little corner, and it's something new drivers don't need to worry about.
That's easy. Next thing. Okay, so anything else anybody wants to throw in? Excellent. Thank you all very much for coming.